Sometime later, that colored liquid will be occupying the new volume, same like the volume, but it's a slightly different volume. I'm going to compare the energy of this chunk of fluid before and after. You realize that in that comparison, the distance between the chain of reagents is common to both the chunks of fluid. Point-wise, the fluid is the same location where the same velocity, so I don't have to worry about that. That's common to before and after. The only difference between final energies, just a bit like here, even part of your fluid is part of the new fluid. It's at the same height going at the same speed, so you don't have to worry about it. So what's the volume? What's the energy of this region? The energy is going to be rho times A2 times delta x2. Delta x2 is the distance in advance of here. That's the volume of the fluid. That's the mass of the fluid. Sorry, that times g is the mass of the fluid. And the kinetic energy will be mass times v squared over 2. Potential energy will be, sorry, I'm doing something right. I think I made a mistake. Sorry about that. That is not g here. Let me do it more slowly. What's the mass of the shaded region? It's got a base A2. It's got a height delta x2. That's the volume. Times density is the mass. And v squared over 2 is the kinetic energy. Potential energy is the same mass times gh. What I call it gh2. We're worried about the height varying over the cube. Yeah, we are neglecting that aspect. That's the important point you can ask. When you say h2, I talk about the middle at the end and so on. But we're going to be dealing with problems where the height differences are much bigger than the cross section of the pipe, so we don't worry about that. Okay, now, what is the same quantity here? It's going to be minus rho a1 delta x1 times v1 squared over 2 plus rho times gh1. That's the final energy minus initial energy. That's got to be equal to the work done. Now, who's doing the work on this? Can you guys understand where is the work coming from? Now gravity, you don't count the force, you have a potential energy for gravity. Gravity is included. If you measure like rho gh or mgh, you don't count gravity again. Okay, but if I'm looking at the fluid in question, who's acting on that fluid? Not what it's doing to others, who are the others doing something to this fluid? Yeah. The walls of the pipe will apply normal force and that will not do any work. Yes. Yeah. Yeah, but that person's somewhere here. But remember, in mechanics, you don't have to go to people in remote places. I told you, in a Newton's law, the only kinds of forces are what? Remember from day one. Yes. This fluid, keep it me. No, I'm talking about this fluid. I'm talking about all of this fluid. My taking the difference of that shade and that shade becomes convenience, but I'm looking at the energy change in all of this fluid. Yeah, but the point is the fluid to the left here is pushing it, and it is pushing the fluid to the right. Okay, that's the only way. If the fluid has a pump somewhere pushing the fluid in the beginning, but you don't have to go all the way to the pump. In the end, you only ask, who is in contact with me? Well, it's the dice to the left. So they will exert the force T1 times A1 times delta x1. Because that's the force, that's the distance, that's the work done on the fluid. And the work done by the fluid is P2, A2 delta x. I'm just using A1, B1 is A2, B2. So if you cancel those factors, what do I get? I'm going to divide it for you, now you guys can go home and check it. P1 minus P2 is equal to 1 half rho P2 squared plus rho GH2 minus 1 half rho P1 squared minus rho GH1. Now this is a derivation that you can go home and study later in any book you like. They're all the same, the story is the same. I can only tell you, if you'd like to know what the circuit behind the derivation was, I don't mind going over that. Because maybe there are different volumes of question you may have gotten confused. But personally, I write down the result. By writing everything with 1 on the one side and 2 on the other side, I get this result P1 plus rho V1 squared over 2 plus rho GH1 is P2 plus rho GH2 plus 1 half rho P2 squared. This is nothing other than the law of conservation of energy.
繰り返しご利用のお客様にご案内いたします。現在も地域における実施を発生中から一番皆さんにご利用の運転をお願いしております。現在入りました情報によりますと、現地での負傷者の救出活動が終了し、現在、警察によります現場検証を行っております。ご利用のお客様にはご迷惑をおかけいたします。運転再開までもうしばらくお待ちください。下り列車1番線、2番線に現在停車中となっておりますが、1番線の列車が2番車となります。
I want you to think about it. This end has moved here, this end has moved there. So the fluid at the end of the day is sitting there. I want the energy of all of these guys minus the energy of all of this. Then you can see the comparison. It's only this part that is gained, and this part that is lost. This part is common. When I say common, not only the mass common, the location, every location, the height and velocity are the same. So in the fraction, this will cancel that, that will cancel that. This will have nothing to cancel. just put on the ball. So let's spin the ball and release it. Then release the extra force. It's rising and falling just on top of the falling to the gravity. Even in a science of gravity, you have this extra force. It's coming simply because the velocity of the top and bottom have been modified. Here's another example. Here's an airplane wing. The plane is going like this. To go right with the plane, in which case the air seems to be doing this. So watch on the plane, everything looks the same. I said the wing was not there, but here's the wing. This is the flow of air past the wing. Notice that these guys, how the wing has to travel further than the particles below the wing, so they can catch up here, but everything is the same. So the velocity on top of the airfoil is faster, therefore pressure is lower. Pressure is lower than at the bottom, then the difference pressure at the area of the wing will push the wing up. That's the lift you get when you start a plane. When you're on the runway, this is where the plane goes up. Once you're airborne, you can tilt your wing. When you tilt your wing, so to this angle, and of course, it's very clear that you can get a component of lift. But I'm talking about when the wing is not tilted or horizontal. That's what you see the lift. Now what if you get a wing that looks like this? Okay, so it all happened. But this has to use to. Have you seen it anywhere? Yes, NASCAR. On the racetrack, you want the opposite effect because you want to push down on the car, and therefore, you manufacture wings. You go to the factory by mistake, it is a wing that looks like this. Then you can bring it to your race car and attach it, then it'll keep the race car down. Of course, you also have the other option of going to the wing and tipping over and applying to the airplane. But if it does not occur to you, if you thought, once the wing is made like this, I'm stuck with this wing, then go take it to your race car and attach it. That'll push it down. If you want to get traction, you can get the upward lift or the downward lift. Now, the test of this lift theory is actually somewhat naive, and I believe it for a long time now. We know the story is more complicated. So there's a lot of truth to this, but it's not the whole story. So if you go there and not get the hearing one day, you will find out that it's a little more complicated reason way to calculate it precisely. But the general notion that when the air moves fast, it loses pressure is true. So here's another example. If you have an atomizer, you have a perfume here, so you got a pump, and then you have a flute here. When you squeeze the pump, the instant you squeeze the pump, you're letting a lot of air here at high velocity. Where the air here is at rest. High velocity air is a lower pressure than low velocity air. Therefore, it'll trap the perfume and spray right on your face. Okay, very good. You know, I've taught you so many things, planets and supernova and galaxies, but now I got it right out of this class. This is, now we're telling you something new. Alright, so now I'm going to do two problems where I really start putting numbers in. This is very quantitative. I'm going to do quantitative problems. And there are only two kinds, so when we're done, we're done. Here's a tank of water. And I poke a hole in this right here. I did that. It's called H. Question is, how fast will the water come out of here? That's how you can use the Bernoulli. That is called Bernoulli's equation. Bernoulli derives. You just have to pick the points 1 and 2 cleverly. It's going to be point 1. It's going to be point 2. Point 2, in fact, is just outside that hole. What does Bernoulli say? C1, which is atmospheric pressure, plus 1/2 rho V1 squared plus rho G H1 is equal to P2 plus 1/2 rho V2 squared plus rho G H2. Let's modify this as follows. Let's fix it to H2 to be 0. Then H1 is just this. You need to pick the 0 in the green light. So grab the whole list and call it 0. So I don't have to worry about this one. P2 is water mass rate. What about P1 and P2? P1 is atmospheric pressure there. And right outside the hole, it's also the atmospheric pressure. So P1 and P2 we cancel because they're both equal atmospheric pressure. I'll put the velocity here. You know that if you punch a hole in the tank and you bring it, it's going to start moving down. But people imagine that's a huge tank, 10 meters diameter, and there's a tiny pinprick. Then this velocity is negative. You can put that back in if you like. I'm just going to ignore that for now. That tells me rho G H1 equals 1/2 rho V2 squared. Cancel the rho, and you find V squared is equal to 2GH. V2 squared is 2GH. Now you remember the formula from day 1. This is the velocity a droplet would have if it spilled over the top and fell straight down. Because that is just 3 NGH, being converted to 1/2 mv squared. Because the law of conservation of energy, the minute the fluid starts coming out of here and going out the top, I have traded droplets of water at the top for droplets of water at the bottom. Therefore, since they have potential energy at the top, they must have kinetic energy at the bottom. But be clear about one thing, the drop coming here is not the same drop moving at the top. If I push it over the top, that would be the same drop, and it's very clear in all of this. The beauty of this is, this water is pushing down and something's coming out here. It's coming out at the right speed, the drop might drop. So the land there. You can imagine the fun you can have with this kind of so that if my dog is standing here, instead of feed the dog, or don't feed the dog, go in front of the dog, go past the dog, hit the biggest rain, smallest rain, or what's the problem? They will combine. This is Bernoulli who will tell you how fast it's coming out, which after one, of how people trajectories, once the fluid is coming out this way. Okay, last topic. It's like inside a new topic, last application of Bernoulli has to do with the, what's called it, eventually needed. By the way, you can imagine this is just a process of possible applications of fluid dynamics. You can take a whole course on fluid dynamics. So let's take the following problem. So you're going in an airplane, and you want to find out how fast the plane is going. How do you think you find out? I'll show you now one device people use to find the flow rate, to find the speed of the plane through the atmosphere. So you go to the plane and you have that forward direction to the plane. So then I can say T1 plus 1/2 rho V1 squared. But rho G H1 I'm not going to write because H1 and H2 are going to be equal. Then it's V2 1/2 rho V2 squared. P2 minus P1 is equal to 1/2 rho P1 squared minus P2 squared. So P1 is the speed of the plane. Now V2 is not the speed of the plane, but you know what V2 is, because V2 times A2 is equal to V1 times A1. So we get right here 1/2 rho V1 squared minus V2 squared is V1 squared times A1 over A2 squared. So pull out the V1 and you write it as 1/2 rho V1 squared times 1 minus A1 over A2 squared. So let's write this formula for a second. In this problem, A1 is bigger than A2, so you write that 1 minus A1 over A2 squared is negative. But so is P2 minus P1, because P2 here is negative lower than P1 here. So if you're happy, you can flip it backwards and write P1 minus P2 or something. You see that? You can flip it over, or you flip it over here. But ask yourself, what do I need to know to find the speed of the plane? Speed of the plane is here. Rho is the density of what? You know what I mean? Rho is the density of what? Yeah, rho is the density of air. A1 and A2 are known because you designed the tube. So if you can find the pressure difference somehow, you can read out the speed of the plane. What people do to find the pressure difference is they go and they punch a hole there, and they put here a fluid. Like oil. If the plane is not moving, you can tell these two heights must be equal. Because sometimes the height is not equilibrium. Because these two pressures are equal. But if the plane starts moving, and the pressure is lower than the pressure here, then if it's high pressure, there's no pressure, it'll push the fluid up, and it'll start looking like this. Because there's extra on the other side. And how much extra is it? Well, let's think about it. The pressure at these 2 points is the same. The pressure here is what I call P1. The pressure here is P2 plus rho P times height of this fluid. This rho is not the density of air. This rho is the density of water. So then the plane begins to move. The pressure will be higher than the pressure here. So the pressure is the
下り列車につきましては、まもなく運転を再開となります。当駅1番線停車中の電車から運転を再開しますが、現在白岡駅に下り列車2本停車しているため、前の列車が動き次第の運転再開となります。運転再開までもうしばらくお待ちください。繰り返しご案内いたします。次の空気の人身事故の影響で、現在電車の運転を見合わせておりますが、再開につきましては、まもなく運転再開となります。